Hi, this is Professor Carter. This is the second video for this first page on the neoclassical production function. So I'm going to call this number one, page number one. Okay, put the little thing there. Okay, as usual, this will be available here. What we saw last, these notes will be available. I'll make copies of these for people to put them under the lectures and make them accessible for the lectures. Okay. Production function we saw, generally speaking, in terms of the neoclassical production function, says that output, newly created output y, is going to be a function of the capital and labor inputs, the factors of production. We are assuming that this is going to be a well-behaved production function. Our output here, we're going to talk more about this um, in future lessons, maybe even get it today, this idea of what it means to be well-behaved. Well-behaved is going to mean that the neoclassical production function is going to have properties that are going to be nice. Nice in the sense there's going to be diminishing marginal productivity. So you have diminishing marginal product of capital, diminishing marginal product of labor, and then when you put the two together, you're going to get a nicely shaped, well-behaved concave, or we said preference, our technologies would be convex. We'll talk about that, but concave to the origin, total products of labor and capital, set par, et cetera, et cetera. And then when you put the all together, you get that nice, well-behaved character. That's what we mean by this. And we saw that when we took the total differential of this production function, we saw that the partial derivatives of output with respect to capital and output with respect to labor are equal to the marginal products of capital and labor, respectively. We're going to come back to that. So that's just a production function in general. One production function that's going to be useful, that Ferguson certainly makes a lot of use of, and that is used in all over economic theory, including in aggregate models, is going to be the Cobb-Douglas production function. All right, so you're going to have the Cobb-Douglas production function in 1928. Charles Cobb and Paul Douglas. Charles Cobb was a mathematician. Paul Douglas was a senator from Indiana, but also an economist. They arrived at and developed this mathematical relationship that is attempts to understand the relationship between output and factor inputs that exhibit the well-behaved character of the diminishing marginal productivity that I discussed earlier. So this says here that output is going to be a function of some shift parameter A. Capital input is going to be denoted to the alpha power, and labor input is going to be denoted to the 1 minus alpha power. The property of the Cobb-Douglas production function is that the sum of the exponents of the different factor prices is always equal to 1. All right, so that alpha plus 1 minus alpha is, of course, equal to 1. That's going to be the assumption of the Cobb-Douglas. There's going to be other production functions that came out after the criticism of the Cobb-Douglas that this lacks realism. They're referred to as the constant elasticity substitution production functions. There, you do have constant elasticity substitution between the different factors of production, a property which also exists in the Cobb-Douglas form, but the constant elasticity substitution production functions are more general in the sense that they're more robust and they can be applicable to a wider range of scenarios than the Cobb-Douglas can, because of the restrictions on the structure of the model itself. We'll talk about that, but really this is a mathematical relationship, and I think it's important to understand that. Now, this is going to be a mathematical function. Okay, so what we're going to do is we've already saw that I introduced in the last video, that the marginal product of capital was equal to the partial derivative of the production function with respect to capital. The marginal product of labor was the partial derivative of the production function with respect to labor. What I didn't say, and what we're going to introduce right here, is going to be that the ratio of these two is going to be this thing called the marginal rate of technical substitution. I'll put it here. Marginal rate of technical substitution capital for labor is going to be equal to the marginal product of labor divided by the marginal product of capital. That's what we're going to talk about now. Marginal product of labor divided by the marginal product of capital. And I'll talk about that. So we're going to be deriving this. So what we need in order to find the marginal products, we need to arrive at the partial derivatives. So we take the partial derivative of your Cobb-Douglas with respect to the labor input. You have here the marginal product of labor is going to be equal to the partial derivative of output with respect to the labor input. This is going to be equal to the change, put here, equal to the change in output is going to be a function of the change in labor input only. You hold the capital input constant. Okay, you take the partial derivative, so you're going to take the first derivative of this function, assuming that the capital input is going to be constant. So you're going to take the exponent, multiply it by the constant, and then subtract that exponent from 1, or subtract 1 from that exponent, like here. So this would be 1 minus alpha times a k to the alpha bar. You're holding that one constant. This is going to be L to the 1 minus alpha minus 1. All right, so that's going to be the first derivative of the Cobb-Douglas with respect to the partial, with respect to the labor input, marginal product of labor, marginal product of capital. This is going to be equal to the partial derivative of output with respect to the capital input here. The quantity of the total change in output is going to be a function of the total change the change in the capital input only. This time you're holding the labor input constant. So you see that in each of these different expressions, I'm holding the different input variable and the other one constant. That's the definition of the marginal product. All right, this now you're going to take your Cobb-Douglas and you're going to hold the labor input constant. So it's alpha times a constant. So it's going to be alpha over a k to the alpha minus 1, L to the 1 minus alpha. You're holding that input constant there by virtue of the partial derivative. Marginal rate of technical substitution, which we're going to come back to in the next lesson, is going to be equal to here. We can establish it's going to be equal to the ratio of the marginal product of labor divided by the marginal product of capital. So you go the marginal rate of technical substitution capital for labor is going to be equal to the marginal product of labor divided by the marginal product of capital. Okay, so then you're going to take the partial derivatives that you've so arrived at here. Marginal product, so there's going to be a fraction. Okay, the marginal product of labor is here. It's going to be 1 minus alpha a to the k to the alpha L to the 1 minus alpha minus 1. Okay, and then in the denominator, you're going to have alpha a k to the alpha minus 1 L to the 1 minus alpha. Okay, and so you're going to have that. So then you're going to break up that fraction. Okay, this is going to be equal to this is going to be, I want to keep my thing here. This is going to be equal to the first bracket. It's going to be 1 minus alpha over alpha. So whatever alpha is, the parameter, you're going to be able to know what that constant term is going to be, or that shift parameter is going to be. This is going to be a over a, right? Here, a over a, well, it goes to 1, that cancels out. This is going to be k to the alpha divided by k to the alpha minus 1, okay? This is going to be L to the negative alpha divided by L to the 1 minus alpha, which is going to be here, okay? So when you solve for that, you're going to have here, it's going to be 1 minus alpha over alpha, k alpha minus 1 minus alpha minus 1 is going to be L alpha minus 1 minus alpha. Okay, when you go through and you do that, this is going to be 1 minus alpha over alpha is going to be equal to here, k to the positive 1, L to the negative 1. This is equal to 1 minus alpha over alpha, k over L. Okay, that's the point. And I know it's a little bit, it's written small there, so I'm going to rewrite it here. We're going to say then that the marginal rate of technical substitution capital for labor in the Cobb-Douglas is going to be equal to, when you have here the Cobb-Douglas form says that y is equal to a k to the alpha L to the 1 minus alpha. Okay, in our Cobb-Douglas form, the marginal rate of technical substitution is going to be equal to 1 minus alpha over alpha times k over L, multiplied by k over L. okay, that's going to be equal to, this is going to be the slope of the isoquant. All right, isoquant. All right, and in the Cobb-Douglas form, it comes out really nicely. So we see that the Cobb-Douglas production function is really a function, a mathematical function that really generates, I'll call this 1.2, that generates the nice neoclassical properties that we're going to be looking at. We're going to be developing that in the next series of lessons. Okay.